notebook over my head, finally. I've been wondering how long you were going to do that for. Check. All right, everybody at home can hear me, can see me, can see my screen, yes?
Yes.
Okay. All right, so here's the deal. It's 9 o'clock, yeah. So here's the deal. You've got the exam that's due on Wednesday. I still have not sent out the link for that, right? I need to send out the actual place to upload the work. And I think it's what, 5 o'clock? Is it 5? Okay, so.
Yeah, you said 5.
Yeah, I'll get that link sent out. Again, we will not have class on Wednesday, but I've already started putting together a video for you to watch. And then there will be some exercises for you to do related to that video. Now, like I said, I'm going to be out of town starting tomorrow afternoon. We're going to be in Houston. My wife's going to be having surgery. So she has a post-op thing going on where they're going to have to remove drains from her. So they said that could be anywhere between 3 days to 8 days. If it's 3 days, then we actually may stay in Houston until Monday and then have the drains removed and then come back. If that happens, then I won't be here on Monday. So we will have a Zoom only class. Okay. That would be the plan. Now, if for some reason that drain removal conflicts with the class, then I don't know what I'm going to do, but I just want you all to be prepared for that. Monday might go to Zoom. Maybe we'll see. Hopefully I'll be back. I don't want to have to drive back to Houston. So like if we have to come back and then have to go back, that would suck, but you know, that's not your problem. So I just want to keep you kind of updated on what's going on. I'll let you all know how things go. Okay. That's exam. Any questions about that exam or anything like that? Okay. Today we are covering, continuing 8.2 series. And we didn't quite finish that. I told you all in class last time that I would send you an email to tell you what problems to do. I forgot to do that. And nobody emailed me. So I'm figuring everyone's working on the take-home test, right? All right, so please don't fall behind here on this series stuff. I mean, you need to keep up with it because it'll be hard to catch up to the train if you let it get too far ahead of you here. All right, so last time we were talking about series, and specifically we started with the idea of the geometric series. That was the first type of series that we need to kind of recognize and be able to find the sum of if it converges. So we went through a bunch of examples, there was like just these, right? We went through these examples and we finished with this really cool kind of way that we can write a repeating decimal or a rational number. We can rewrite a repeating decimal in its fractional form. And that's where we stopped. So we are going to now continue with the next topic, which is harmonic series. You should have those notes. I gave those to y'all last time. And then if you're here, there's notes up here if you didn't get them for both 8.3 and 8.4. At home, I have uploaded both of those into that folder where our notes are for the class. So if you have those, you may need those when we move into 8.3 today. Okay, you ready? All right. So I think part of what makes this chapter so hard is that there's so many little subtle definitions and terminology that you have to know, right? The main kind of idea is that if you have an infinite series, we want to be able to figure out whether or not it converges or diverges, right? Convergence or divergence. And right now, the only thing we have really is that nth term test, that pregnancy test thing, right? We have that, which really at the end of the day kind of sucks because it doesn't, for most of the time, it doesn't help us, right? But we have it. And then we know if we have a geometric series that it will converge so long as the absolute value of r is less than 1, diverge otherwise. So that's where we are. Now we're going to look at another type of series And it's really actually a nice series. It's called the Harmonic Series. And it's like harmonic is like the best series ever. Because as soon as you see it, you know it diverges. Like there's no test, there's nothing you need to do. It diverges all the time. So what does a harmonic series look like? It's any sum, okay, from n equals 1 to infinity. And all you have to be harmonic is a constant, so some number, on top of some linear expression in n. That's it. As long as you have a constant over a linear expression in n, it's harmonic, it's going to diverge. So the examples we have here, this first one, 1 over n, right? 1 is a constant, n is linear, that's harmonic, it's going to diverge. Now I'm going to prove to you why, but let's just look at what they look like. Here's another one, 4 over 2n plus 1, right? Harmonic, constant over a linear expression in n. Next one, -5 over n plus 5. N plus 5 is linear, right? Numerator is a constant. These are all harmonic. Understand? Pretty easy to identify. Cruz, what's up? Yeah, okay. You just look like you had a question. Okay, so now let me try and prove to you why a harmonic's going to diverge all the time. It's kind of a weird proof. I have two ways of proving this. This proof, and then when we get to the next section, we're actually going to have a test that we can run. And if I run that test on a harmonic, it's easy to show it diverges. But let's not do the test. Let's do it this way. So, whoa, hold on. Something's up with my thing, doesn't want to write on the right screen. Hold on. All right. Stand by. I got to unplug this, plug this back in. See if that fixes it. There we go. Okay, let me reshare my screen. Okay, we all good? We back? At home, you got my screen?
Yep.
Okay. All right, so here we go. We're going to take the most basic harmonic series there is. Sum n equals 1 to infinity of 1 over n. I'm going to try and convince you that this diverges, all right? So the way I'm going to do it is I'm going to start writing out the terms of this series. 1 plus a half plus a third. Actually, I'm going to do it below here, and I'm going to write a bunch of them out, okay? 1 plus a half plus a third plus a fourth plus a fifth, sixth, seventh, eighth. I'm going to go all the way out to 16, okay? Plus 1/9, 10, 11, 12, 13, 14, almost there. Should have done this before class. 16 plus ... Okay, it keeps going forever, right? Okay, so here's what I need you to kind of recognize. First of all, if I take, I'm going to highlight or I'll underline these. 1 is 1, right? Okay, 1 is 1. Fine. Plus, now 1/2 is 1/2. Great. I want you to now look at the next two together. I want you to put those together with a common denominator. So what would you get if you had a common denominator between those two? What would the fraction be?
7 over 12.
7 over 12, right? You get 7 over 12. So this is going to be 7 over 12, right? Okay. Let me see. What if we take the next? You might need a calculator for this. What if we take the next 4 of those together? What would you get? So did any of you have a calculator that does this symbolically? So you can, a fractional answer? 533 over 840. Okay. Next, I want you to do not, okay, so we did the first two together here. See that? We did those two and we got 7/12. Then we did the next four and we got that, okay? And now I want you to take the next 8. I think that should be 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's 8 of them. So we took 2 of them here, 4 of them here, and now we're taking the next 8. Now, unfortunately, I need someone to add that up for me. Got Christian plugging away here. While that's going on, here's something you can think about, all right, that might help you understand this a little bit better. Look at these 4 that we put together here, okay? See the one on the far right is 1/8. Isn't the one to the left of it a little bit bigger than 1/8? 1/7 is bigger than 1/8, isn't it? And isn't 1/6 bigger than 1/8? And isn't 1/5 bigger than 1/8? So would you agree with this? This is bigger than me adding 4 1/8 together. Wouldn't it be? Wouldn't this sum right here be bigger than me just doing 1/8 plus 1/8 plus 1/8 plus 1/8? Right? And what is 1/8 plus 1/8 plus 1/8 plus 4 of those? That would be a half, right? 4/8, which would be a half. Okay, same idea here. The one on the far right is 1/16. 1/15 is bigger than that, right? And 1/14 is bigger than 1/16, and 1/13 is bigger than 1/16, and I could keep doing this, right? So if I were to instead do 1/16 8 times, right? 8 times, wouldn't that be 8/16? And this would be a half. But this is bigger, right? What's down here is bigger than a half. Understand? And then if I continue down, right, I go dot, dot, dot. If I take not the next 8, but I take the next what? What do you think? The next 16 of them, the last one's going to be 1/32. And each one before it is going to be bigger than 1/32. So I can take 16 1/32, which is a half. Does that kind of make sense? So tell me if you agree with this. This number is bigger than a half. This number is bigger than a half. And all of those together, right, would be a number that's bigger than a half. So isn't this sum that we're trying to find bigger than 1 plus a half plus another half plus another half plus another half plus another half forever? But what's a half plus a half plus a half forever? That's infinite, right? That's infinite. This sum goes to infinity because you see that these terms are not headed to 0. So you could almost do like an nth term test on it. This sum right here is the sum n equals 1 to infinity of just 1/2. See, there's no n in there. It's just 1/2 plus 1/2 plus 1/2 plus 1/2 forever. That will diverge. And our sum must be bigger than that. Does that make sense? That's it. I mean, that's the rough proof of it. So it's kind of cool. You have to see the pattern that you take the first 2, then the next 4, and then the next 8, then the next 16, then the next 32, then the next 64, then you go 128, then you go right, and you just keep doing that forever. You'll never run out of terms. Yeah. Okay, so that's it. Any questions? All harmonics diverge. All right, so good. We can, this is kind of a proof. Here's 1 over n. So you can see that I showed this to you last class. The one on the left is the sequence, 1 over n, and the one on the right is the series. And you can see that the further I go out, of course, the sequence 1 over n goes to 0, but the series starts to grow. And you can see that it's growing slowly, but it is growing. And the further I go out, that will head to infinity. Okay, the next type of series that we need to be able to work with is called a telescopic or collapsing series. Now, unfortunately, this is not like a harmonic, okay? This isn't just you look at it and go, oh yeah, it diverges, yay. No, telescopic collapsing series, these series suck, okay? They're gonna be a lot of work. But there's one good thing about telescopic and collapsing series, and that is, if they converge, if they do, we can find the sum. There are only two series in this class that we will be able to find the sums of. Geometric, when they converge, we have a formula for it, a over 1 minus r. We did that last class. So we can find the actual sum of a geometric series if it converges, and we can find the sum of a telescopic if it converges. Every other series we deal with, we won't be able to find the sum, okay? So the only way to really illustrate this telescopic is to show you an example. I mean, there's no like set of notes. I guess I could write up notes on how to go about these, but it would look real bad. Those notes would look really ugly. So this is your first example of a telescopic or collapsing. You'll see why we call it telescopic or collapsing. You'll see why we do that after we go through the example. So I just want to remind you of something, okay, from our notes from 8.2 in the very beginning. And that was, you know what, let me show it to you because I think it's worth you seeing it. In 8.2, right here, early in this section, I did a quick little recap right here. Let's clarify, right? I said, hey, if you're given a series, right, then S sub n is what we call the nth partial sum. So what we're doing is we're not adding up all of them, we're only adding up n of them. Then that creates a new sequence of numbers, S sub 1, S sub 2, S sub 3, S sub 4, all the way out forever. So if this series has a sum, then what the sum will be equal to is the limit of that sequence S sub n. So if we can ever come up with a formula for S sub n, the nth partial sum, if we can come up with a formula, all we need to do is take the limit of it as n goes to infinity, and whatever that is the sum of the infinite series. The challenge is coming up with the formula. That's the hardest part, is how can you come up with a formula for S sub n? So if you look back at the lecture last time, we tried to do it for geometric, and we actually were able to come up with a formula. It was a very clever move we made to do it, but we came up with a formula for S sub n. We're going to try to do the same thing here. We're going to see if we can come up with a formula for S sub n. If we can come up with a formula for S sub n, we'll take the limit and hopefully it'll converge. All right, so we look at this sum. Let's just start writing out the terms of this series. If I plug in 1, I get 1 over what? 2? Sorry, Christian, I never asked you for that answer. You went and plugged all those numbers in. I'm sorry. Okay, plus someone else did too, right, Cruz? Sorry, I apologize. All right. Yeah, you know what it is, ugly. Okay. So now plug in 2. Let's see, we get 1 over what? 6, 1/6 plus, okay, let's go 3. 9 plus 3, right? So we're what, 1/12? Let's do one more. 4, 16 plus 4, 1/20th plus ... Now, real quick, nth term test. Take the limit of the sequence. It goes to 0, right? Tells you what? If the sequence goes to 0, what does it tell you about the series? That you don't know. Okay, that's the thing about the nth term test. You have to use it correctly. You look at that sequence, 1 over n squared plus n. Let n go to infinity. That goes to 0. You don't know shit. Okay, you don't know anything. If it went to, let's say it went to 1, then you know something. Then it diverges and you're done. Okay, so these are all going to, like, these are getting smaller and smaller, right? They're going to 0. That's not enough to tell me anything. I told you that first time we looked at nth term test. If the nth term test said that if it went to 0, it converged, then chapter 8 would be easy, because then we would always just be able to check, right? But it's not enough. All right, so here we go. What the hell do we do with this, right? What do we do with this? So here's something very kind of, I'm not going to say it's unnatural, but you're not going to want to do it. You can factor the denominator, can't you? And if you can factor that like that, then you can do partial fraction decomposition on it. like a rational function like you did when we were doing integration and trying to split that thing up. So I'm going to do that on the side over here. I'm going to do partial fraction decomposition on this. So I've got 1 over n times n plus 1. Those are two distinct linear factors. So I can rewrite this as a over n plus b over n plus 1. Y'all understand what I'm doing? And then you go try and figure out what a and b are. So let me run through this. I don't want to show all the detail because we've done this before, and I trust that you could do this on your own. Clear the fractions. Here I'm going to do the shortcut method. I'm going to let n be 0. And if I let n be 0, that'll kill off the b term. So if n is 0, you should get a as 1. And then I'm going to let n be -1. And if I do that, I should get that b is -1. So I'm really glossing over that real quick, right? But are y'all understand what I'm doing there? You could do that on your own. Yes. Okay, so that means I can rewrite this series this way. I'm going to scroll down a little bit. This means that series can be rewritten as sum n equals 1 to infinity. But now I have two terms in there, right? Two things. I have a over n, so 1 over n. And then I'm going to put plus, now b is -1 over n plus 1. So look, that is the same series. It's just we've rewritten the formula in the middle, not in the middle, the a sub n, this formula that we had, all we did is just some algebra on it and just wrote it in a different manner. They're equivalent, okay? Because all I did was split them up. But when you start writing out the terms now, look at them, they're different, they look different. Okay, so watch what happens. If I start plugging in values, okay, let's plug in 1. I'll get 1 over 1 plus -1 over what? 2. So I plugged n as 1. Plus, now I'm going to plug in n as 2. I get 1/2 plus -1 over 3 now, right? Plus, now plug in 3. I get 1/3 plus -1/4. Plus, now I plug in 4. I get 1/4 plus -1/5. Plus dot, dot, dot. That keeps going forever, doesn't it? Do y'all see it? Do y'all see what's happening here? We've got 1, and then we got -1/2 plus 1/2, -1/3 plus 1/3, -1/4 plus 1/4, -1/5. Wait a minute, there's a bunch of stuff going away here, isn't it? A bunch of stuff is canceling. So we look like we have something happening where all these terms are starting to kill each other off, right? So that's a good thing, all right? That's a good thing. I'm going to stop here. And this is important when you do your final exam. You need to do this step. You don't do this step, I'm taking off a lot of points. We have to come up with a formula for S sub n. This is what I don't want you to do. Don't do this. Answer is 1. Right? Everything else went away. You can't do that. All right? You cannot do that. And it's tempting, but you can't. All right? What you have to do is come up with a formula for S sub n. So S sub n, isn't that just the sum, but we stop at n? We stop somewhere, right? Instead of letting it go forever. So what I'm going to do is I'm going to rewrite everything again. 1 plus -1/2 plus, and then 1/2 plus -1/3 plus 1/3 plus -1/4 plus, then I'm going to put dot, 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 okay? But it's not going to go forever this time. I'm going to stop it at n. So at the very end of this, I'm going to put a final term out here that is what I would get if I plugged n into the formula. But isn't that just the original formula? It's just 1 over n plus -1 over n plus 1. Agreed? That's the last one. That'll be the last one if I stopped at n. Now, very important. What's the one before it? What would the term before it be? So if this is 1 over n, right? If this is 1 over n, what would the 1 in front of it be? So go back here and maybe you can see the pattern. It's kind of an easy pattern here. If this is 1/3, the 1 in front of it, the first term in this parenthesis would be 1/2. And if you go over here, this one would be 1 over 1. Isn't it just 1 less? It's just one less, right? So this is just 1 over n minus 1 plus negative 1 over, and then same thing. It's one less than this. So just 1 over n. Yeah? Let me ask you, could you tell me what the one in front of that one would look like? So 1 over n minus 2 this time plus negative 1 over n minus 1. So every time you go backwards, you're just taking one more away from the n. Everyone clear on that? No questions? I want us to talk about what we're seeing. Like, let's verbally explain what we're seeing. Okay, so let me explain it. Let me explain it the way that I see it. The way I see this is that when you look within a parenthesis, right? When you look within one of those parentheses, you have a first term and a second term, right? What I'm seeing is that the second term will cancel with, ooh, my handwriting is much better in this. I still have not gotten used to writing on like a glass screen. It's so slippery. Okay, second term cancels with the first term one set down. Okay, what do I mean by this? I mean, when I look at these parentheses, I notice that the second term, right, the second term in a parentheses will cancel with the first term in the parentheses one set down. One set down, one set of parentheses down is what I mean. The reason I'm pointing that out is because in the next example, it might be 2 or 3 parentheses down that you get the cancellation. It doesn't always have to be right next door like that. All right. So I'm seeing this pattern that second guys are killed off by first guys one set down. All right. Second terms are killed off by first term. Another way you could say that is that the first term is cancels. God. Cancels with the second term one set upstream, right? Not downstream. So like if you're a first term, go to any first term anywhere you want here. Like let me go to that first term, right? That first term is going to get canceled with what? The second term one up, right? Not one down, but one up. So that one cancels with that one. So if we have those patterns established, let's go ahead now and start canceling things, all right? So the blue ones cancel. I'm going to do those in black here. Those are gone, right? Those are gone. What about this negative 1/4? Is it gone or not?
Yes.
It would be because it's a second one, right? And second ones cancels with first ones one set down. Well, is there a set down from this? Somewhere in that ... it's there, right? So I can cancel this one. And everything in here is going to be doing the same thing. Cancel, cancel, cancel. Then I get to this guy right here, 1 over n minus 2. Now this guy, that's a first one, right? First ones cancel with second ones one set up. So is there a second term one set up from this? Yeah, somewhere in the ... right? So this one cancels with something in here. This one cancels with something in there. Understand? What about this one right here? Negative 1 over n minus 1. It's a first one, right? So it's got to cancel with the one. Sorry, it's the second one. Sorry, it's the second one in the set. It's going to cancel with the first one down. So they're gone. Those two kill each other. Okay, this one right here is the second one. It cancels with this one, right? This and this, they're gone. Now, what about the last one? Doesn't have anything to cancel with, right? It's a second one. Second ones need a first one down, but we stopped, didn't we? We stopped. So this guy is still here. And at the very beginning of the series, this guy was here, right? The one in the front never canceled with anything. What has happened to all the stuff in the middle? It has collapsed, right? Collapsed away. It's like a bridge. The two ends of the bridge stayed. Everything in the middle collapsed. All right. That's where it gets the term collapsing. Now, telescopic, it comes from the term, the old telescopes, the old handheld telescope, it was like, you know, they would pull them out and then look, and then when you put them together, right, and everything in the middle goes away. So it's like the same thing, old style telescope, the two ends come together. That's what we have here, all right? So we have S sub n is equal to 1 plus -1 over n plus 1. We have a formula for S sub n, right? Everything else is gone. And so the final step is take the limit of that. Take the limit as n goes to infinity of this expression. And fortunately for us, the answer is 1, which is what I said you would have gotten in the beginning if you did it wrong, right? You got the right answer this time, but it doesn't always work that way. Sometimes this thing at the end will not converge to 0. Like this thing might go to infinity. And then in that case, this series diverges, all right? Make sense? All right, let's do another one. All right, so we're starting to add a lot of layers on here now, right? Starting to feel a little bit like the integration where you had all these techniques, right? So we look at that, we're asked, does this converge or diverge, right? That's what it's asking. Well, I didn't copy the question, but it says show this converges or diverges. So I look at that and let's just start from scratch. First thing I do is the nth term test, right? I'm just going to run the nth term. I'm going to do it in my head. If I let n go to infinity in that yellow expression, it goes to 0. That tells me absolutely nothing, right? So that means I need to keep going. Is it geometric? Is it a geometric series? How can you quickly tell me it's not? What do you need for geometric? Think about what they look like. Sum a r to the n minus 1, n equals 1 to infinity, right? That was the form. Also, at the end of the class last time, I told you there's another form where you start at 0 instead of 1. And the only thing that changes is that n minus 1 becomes an n. Those are equivalent. So what is it that makes a geometric series geometric? I mean, like, what is where's the n? N is a power, isn't it? In a geometric series, n is an exponent. It's not in the base. The base is a number, it's r. So when we look at this, n is not in a power, right? So it can't be geometric. Is it harmonic? No, we have a constant on top, right? But we don't have a linear expression on the bottom. We do not have a linear expression. So we have to figure out what's going on here. Oh, I should point this out. Very important. I kind of forgot about this. Didn't put this in the notes either. When we got here, look at this. When we got here, if I asked you to look at those two individually, aren't they both harmonic? And wouldn't you tell me that they both diverge, right? But what you're doing there is you are assuming that you could split this up into two series like this, right? And then just say, oh, harmonic, harmonic, diverge, diverge, it diverges. That would be wrong. The reason why it's wrong is because you are assuming you can take a sum of two things being added and split into two. You cannot do that. It's not allowed unless these two individually converge. If one or both of them diverge, you're not allowed to split it because you run into the danger of making a conclusion that you diverge, even though it converged, didn't it? It converged to 1. So don't ever split a series up. When you have addition here, don't ever split it up unless you can guarantee me that these two individually are convergent series. Okay, so this is not okay. No, no. All right, so it's not, nth term test fails, not geometric, not harmonic. Well, the only other thing we got is telescopic at this point, right? And I see that the denominator factors. So I'm going to factor the denominator. -4 over n times n plus 2. All right, I've got to go do some partial fractions on that. Has anyone done it yet? No? -4 over n times n plus 2. Again, those are linear on the bottom, so a over n plus b over n plus 2. Get a common denominator, so -4 equals a times n plus 2 plus b times n. Let n be 0. If n is 0, we should get a is -2, I believe. And if n is -2, that'll kill off the a term, and we should get b is +2. Can someone confirm that? I don't want to get too far.
Yeah, that's what I got.
Okay, good. All right, now we just now rewrite the sum, right? We rewrite this sum, n equals 1 to infinity. And we're going to write it as a, which is -2 over n, plus b, which is 2 over n plus 2. Again, individually, these are harmonic, but we cannot look at it that way. We can't split this up into two sums, all right? We're not allowed. So we're going to instead just start writing out the terms and try and find a pattern. Here it comes. Plug in 1, I get -2 over 1, plus, I'm plugging in 1, so 2 over 3, 2/3. All right, I just plugged 1 in there. Now I plug in 2. So -2 over 2 plus 2 over, what, 4? Notice I'm not reducing these fractions. I'm just leaving them like that because that'll help me see cancellation. Now I plug in 3. So we get -2/3 plus 2 over 5. We good on this? Y'all seen this? Plus -2 over 4 plus 2 over 6. We'll do one more. Plus -2 over 5 plus 2 over 7 plus ... forever, right? It keeps going. Do we have a canceling pattern? I'm seeing this guy right there and that guy right there. I'm seeing this guy and this guy and that guy, right? So let me try and write this out. I'm going to say that second terms cancel with first terms. How many down? It's not
2.
right next door, right? It's not the parentheses right next to it. It's actually 2 parentheses away, right? So 2 down. Or I could write it backwards. I could say first terms, right? First terms cancel with second terms to what? Up this time, right? You kind of reverse it. What next? S sub n. I need to see S sub n. You've got to rewrite this and stop it somewhere. All right, so let's rewrite this and stop it. Yeah, okay. -2 over 1 plus 2/3 plus -2 over 2 plus 2/4 plus -2 over 3 plus 2/5. I'll do one more. -2 over 4 plus 2/6 plus ... plus, and now I start at the very end. What's the very last term we have over here? It's what you get when you plug n into it, right? So it's just the original formula here. -2 over n plus 2 over n plus 2. How many before this am I going to need to write? At least 2, because that's where I'll see the pattern of canceling. If I don't put 2 of them, I won't see it. So what's this term? -2 over n minus 1, and then 2 over n plus 1. So you're just doing one less than each of these denominators as we go backwards. And then just do it one more time. -2 over n minus 2 plus 2 over n. I'm going to go through these one at a time and just kind of see what goes away. So let's start with the very first one, -2/1. That is a first term, right? This one right here, this is a first term. And what do you have to have for a first term to go away? A second term, but 2 up, right? 2 upstream. So is there anything upstream from this one? No, this one stays, right? That stays. Let me look at the next first term. I'll come back to this one. What about this next first term, -2/2? It's a first term. You need a second term 2 up. There's nothing 2 up, right? So that stays. Let's look at the next one, -2/3. You need a second term 2 up. We do have that one, right? This one is going to cancel with that one. What about the next second term? I'm sorry, the next first term here. This one cancels because you go up and it cancels there. All right, let's do the same thing. Let's stay on this side and let's do now the second terms. How about this second one, 2/5? Is it going to go away? Yes, it's going to need a first term 2 down, and 2 down is in the ... So this is going to cancel with something in there. What about the 2/6? Cancel with something in the ... Understand? What about this backside? Let's start at the very end. This is a second term. A second term needs a first term 2 down. Do I have, for this one right here, this second term, do I have a first term 2 down? No, right? There's nothing downstream from this. We stopped here. How about this one right here? This 2/n+1, that's another second term. Do we have a first term 2 down? No, right? Those two stay. How about this 2/n? It's a second term. We need a first term 2 down. Well, there it is. Right there, they're gone. What about this first term right here? You need something 2 up, don't you? And we do have 2 up. It's somewhere in that ... And then this one right here cancels with something up here in the ... I forgot to put S sub n on the front of this, sorry, S sub n. So S sub n is equal to -2 -1. So I just took these first two, that's -2, that's -1. And then plus 2/n+1 plus 2/n+2. And now I take the limit as n goes to infinity of this, and that should just give me -3. Do you get the idea of these telescopics? So far, partial fractions, establish the pattern, S sub n, write it out, cancel, see what's left on the two ends. That's S sub n, take the limit as n goes to infinity of that. All right, I'm going to give you like 5 minutes to see what you do with this last example. I'm going to help you get started. Let's just real quick run the nth term test to make sure we're not wasting our time. If you let n go to infinity here, natural log of, well, you get infinity over infinity, right? So you could run a quick L'Hopital on the inside. What would L'Hopital on the inside give you?
3/1.
1, right? You get a 1, 1/1. And natural log of 1 is 0. So the nth term test tells you nothing. Got it? It's not, it is not geometric because you don't have n in a power, and it's definitely not harmonic because you don't have a constant over linear. So at this point, all you have is telescopic. But it also is not partial fractions. Let me give you a minute. Think about maybe, like if you started writing the terms out right now, right? If you started writing terms out, what would you get? I'm going to give you like 3 minutes. Question. You ready to talk? If you just start plugging in n's, nothing's canceling, right? Because you just have something plus something plus something. So does anyone have an idea what we can do?
Split the natural log into the numerator minus the denominator.
Exactly. So remember property of logs. We have this property, if you have natural log of x over y, you can split this into natural log x minus natural log y, can't you? That's just a property of logs. So I can rewrite this if I want as natural log of n plus 3 minus natural log of n. Now, individually, if you were just asked to find this series, you would say that diverges, because if n goes to infinity here, that would not go to 0. So the nth term test would tell you that goes to infinity, right? That diverges. But again, you can't split, you can't look at them individually because they don't converge. So we have to just treat it like this. Now, when you plug in, what happens? Start plugging in values of n. You're going to get natural log 4 minus natural log 1 plus natural log 5 minus natural log 2 plus natural log 6 minus natural log 3 plus natural log 7 minus natural log 4 plus natural log 8 minus natural log 5 plus ... forever, right? Do we get canceling? We do. Look at them. This one, way down here with that one. So that would be first ones kill second ones. How far down? 1, 2, 3 down. The first kills the second, 3 down. Another way you could say that is that second kill the first, 3 up, right? That's the pattern. Yes. On a test or something, I would never have you go further down than 4. Yeah, I mean, but theoretically, if this was natural log of n plus 30 on top, right? N plus 30 over n, then you wouldn't get the cancellation till like 30 down. I wouldn't do that to you, but I mean, that could happen. So what comes next? S sub n. So S sub n equals natural log 4 minus natural log 1 plus natural log 5 minus natural log 2 plus natural log 6 minus natural log 3. I'm probably going to run out of room here. Plus natural log 7 minus natural log 4. I'll stop there because there I get at least one of the cancelings in there. Plus ... I really think I'm going to have a hard time squeezing this in here. So I'm going to do it on the line below. The very last term is natural log of n plus 3 minus natural log of n. The one before that is natural log of n plus 2 minus natural log of n minus 1, right? One less on each of these n's, plus the one before that, which is going to be natural log of n plus 1 minus natural log of n minus 2. One more. Natural log of n minus natural log of n minus 3. plus, and then the dot, dot, dot is before that. Make sense? All right, so this first one canceled with that one. Let's just keep going with first ones. Is this first one natural log of 5 gone? Yes, that kills off with something in the dot, dot, dot. How about the natural log 6? Yes, something in the dot, dot, dot. Natural log 7. Yes, something in the dot, 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 right? All those first ones are gone. How about second ones? Second ones need a first one 3 up. So this guy's not going anywhere, right? This guy's not going anywhere, and this guy's not going anywhere. Those 3 stay. How about on this end, the other end of the finite sum here, this partial sum? How about natural log of n? Let's start with that. Yeah, right. That gets killed off with that one down there. How about the next first one? This natural log of n plus 1. I need a second 1, 3 down. I don't have a second 1, 3 down. This one stays, doesn't it? So does this one. This one doesn't have 1, 3 down, and neither does that one, right? All of those don't go away. Now, what about the second ones? These. Those get killed by the dot, 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 don't they? Yeah, that covers it. So everything in yellow is still there. On your test, this is kind of what I expect to see, right? Like you kind of working through this, showing me the cancellation. I really would like it if you told me the pattern, at least, you know? So now, what is S sub n? S sub n is negative natural log 1 minus natural log 2 minus natural log 3 plus natural log of n plus 1 plus natural log of n plus 2 plus natural log of n plus 3. And now when I take the limit as n goes to infinity of S sub n, what do I get? It diverges. It's infinite. Look, you're trying to figure out what happens to that as n goes to infinity. Natural log, it goes slowly, it grows, right? That goes to infinity. That goes to infinity. That goes to infinity. All those go to infinity. These are all finite, right? Those are just numbers. So you get some number and then you keep adding these bigger numbers. This is going to diverge. So this is an example of a telescopic that diverges. Not all telescopics actually collapse down and everything goes away. So when you are taking a test, all right, this is important. When you're taking a test, if I give you a series and I tell you, find the sum, what do you know right off the bat then? It's convergent, yes, and it's either a telescopic or geometric. That right there, that's a hint on a test. If I tell you find the sum, you know right then it's either geometric or telescopic. Because I can't ask you to find the sum of any other series. Now, if I ask you to tell me if it diverges or converges or diverges, then it could pretty much be anything. All right. So usually on the test, you'll have 2 problems on the final that'll say find the sum. And one of them is geometric and one of them is telescopic. All right. A harmonic. Yeah. Harmonics are going to come up. Trust me. They will come up. It's a very useful thing. All right. We good? All right. You know what? I said this at the end of class last time, but I'm just going to restate it. It's the last thing for this section. We already saw earlier what a geometric series looks like. So the idea is that when you plug in 1, you get A, you plug in 2, you get AR, plug in 3, you get AR squared. If we re-index this, that means we start our sum at 0 instead of 1. Then if we adjust our formula to just be n, power n instead of n minus 1, it will create the same exact series. You can check for yourself. Plug in n is 0, then 1, then 2. So when we started chapter 8 and we were talking about sequences, I said a sequence is a function that goes from the natural numbers into the real numbers. I said we'll always start at 1. We are now going to loosen that restriction. Now a sequence can go from the integers into the real numbers. So you can start your index anywhere you want. Start at 0, start at 1, start at 5, start at -2. It just doesn't matter where we start it. It's just that with the sum, it just keeps going up by 1 each time you plug in a number, right? So you start with n is 0 here, then n1, then 2, then 3. All right, please recognize these as geometric, all right? Questions? We're ready to move on to 8.3. So our first section in series is done. Yep. It gets easier now. Yes, it gets much easier. Well, I wouldn't say it gets harder. You know, it just gets more complicated. That's a nice way of saying it gets harder, right? So here are the notes for this. See, maybe I can go a little bit bigger. All right, 8.3, the integral and comparison tests. So now we're going to talk about two more tests. What tests do we have right now? Do we have any tests right now? We have the Nth Term Test, right? That's it. That's all we've got. That's the only test that we can look at a series and do this test, and we can tell if it diverges with the Nth Term Test. We have no test for convergence yet. We know if it's geometric, we can figure it out. If it's harmonic, we can figure it out. If it's telescopic, we can figure it out. But otherwise, we don't have any tests. So now our first two tests, or our next two tests, the integral and comparison tests. So these are two different tests. The first test, the main idea, right, is that we can only find the sum of geometric and telescopic, right? I already said that. In general, finding the sum of a series is really hard to do. So as we progress into this chapter, all we need to be able to tell is converge or diverge. That's it. It's a thumbs up or down. And I know that you may be like, well, that seems like that's stupid, because wouldn't we like to know what it adds up to be, right? I mean, like, but it turns out later, the convergence and divergence is really all we need, okay? So preliminary idea. We are trying to determine the convergence or divergence of a series. I just alluded to this, but I need to really make sure you understand this. Let's say we have a series, right, that starts at n equals 1 and converges. What if I tell you that, okay? I've got this series, starts at 1, goes to infinity and converges. Then if I ask you to start at 5 instead, does it change the fact that it's still convergent? Shouldn't, right? Because what we're saying is if you add up all of them from 1 to infinity, it's finite. You get a finite number. So if I then tell you to take off the first 4 and look at those from 5 to infinity, that should still be a number. Those 4 finite terms shouldn't make a difference, should not impact the convergence. Same with divergence. If I tell you that you add up all these things and it diverges, if you take out the first 4, it's still going to diverge because the first 4 is a finite number. Understand? Now, if you do this, if this converges to a number, right? If that converges, then it goes to some number that we don't even know. This will also converge, but to a different number. It's not the same number. It's just, it's convergent. Yes? Just, we don't care about the number. We just care about the fact that it converges. Okay, here we go. The integral test. So we got to do this. I'm going to do it visually first. So remember from Cal 2 earlier this semester when we were doing improper integrals, when we learned about definite integrals, right? We said, oh, if you put two numbers, then you have the area under a curve. But what if one of those limits of integration was infinity? That means you're finding the area under the whole graph all the way to the right. Well, I want you to think about that. If we have this improper integral, then what it represents visually is just, this is too big. I've got to back out here. It's just the area underneath this curve, right? We've got this curve and we're trying to find the area from 1 to infinity. Yes? All right, so let's say that we have a function. In this example, it's 1 over x squared. This function is continuous on the interval 1 to infinity, meaning that when we draw it, we can draw it without picking up our pencil. It's nice and smooth, right? That is a continuous function on the interval from 1 to infinity. Y'all agree? It is also positive, meaning it's above the x-axis. This graph is above the x-axis, yes? okay? And it's decreasing, which means that as you move from left to right, it goes down. Let's say we have that, a function that's continuous, it's positive, and it's decreasing on that interval. With me? All right. Then what if we look at, this is the function 1 over x squared. What if we look at the series that has as its terms a sub n equals 1 over n squared? What's the difference between 1 over x squared and 1 over n squared? This is the actual curve, right? And this is just the dots along the curve at 1, 2, 3, 4, right? That's all it is. So if we look at that, I need to make this a little smaller. Can't quite get to my controls here. Then here's what I would like for you to do. Let's think about the area underneath that curve, okay? That we can do. We can do that integral, right, to get that area. But instead, I want you to create the sequence that goes with that. And at each of the points on the sequence, so the blue dots are the sequence. This is supposed to be f of n equals 1 over n squared. Sorry, that should be an n squared. These dots, this is 1 over 1. This is 1 over 2 squared. This is 1 over 3 squared, 1 over 4 squared, 1 over 5 squared, right? I want you to create rectangles out of these dots. So I want you to go to, on each one of these dots, I want you to go up to the dot, go out to the left, make this 1 unit wide, and then come back down. Wouldn't the area of this rectangle right here be equal to 1 times how tall it is, right? And then this one would be, the area would be 1 times how tall that is, which is the sequence value. And I keep doing that forever, right? Then isn't the area of all of these rectangles here, isn't that area smaller than the area underneath this function? With the exception of this one rectangle right here. Y'all see this one rectangle? That's not under the function, is it? I went up to the first one, and I went over and down. This is not underneath that function's area. But isn't this rectangle finite? Isn't it finite? This is just, I mean, whatever the area of that is, it is. But all of these here, all of these areas together must be smaller than the area underneath that. So what if we are able to determine that the area under this curve is finite? What can you tell me about the series then? It has to be finite too, because what we're doing is we're saying that the sum of all these rectangles must be smaller than the sum of that area, which it would be if that goes to a finite number, plus this rectangle. Okay, but that rectangle is finite. Does that kind of make sense, the idea? So I'm gonna give you the actual integral test. I want you to see it visually though. But what if this diverges? What if this is infinite? Wouldn't that, would that force these to be infinite? So let's say the area under this function, let's say it was infinite. And you're telling me that the sum of all these rectangles is smaller than infinity. Does that mean that it has to be infinite? No, the number 5 is smaller than infinity, isn't it? It's not infinite. All you'd be able to tell me is that the sum of those rectangles is smaller than infinity, which means it could be anything. It could be finite or infinite. So that's not enough, right? Right? It wouldn't work. Do you understand the difference? If the area under this function is finite, then this sequence, right? This sequence would be finite also. But if this area is infinite, this won't work. So let me do something else. I want you to do the same idea, okay? But this time, instead of drawing your rectangles the way I had you draw them here, where you started, you went up to the point, and you drew out to the left and down, I want you to go up and draw to the right and down instead. If I do that, it'll look like this. Here's the area under the curve. By the way, 1 over x, that is a divergent function. So if you go out, we did that in class, but don't worry about that right now. If I go up here and I go up and to the right, and then I continue doing that forever, now the sequence, right? All these rectangles, the areas are bigger than, you put all those together, it's bigger than the function's area. So now if the function's area underneath is infinite, then the sequence has to be also. Make sense? It's just how I drew the rectangles that matters. So this can be confusing, but let me just kind of go back up here. Let me give you the test. Let me actually go down here and give you the test. Here's the integral test conclusion, all right? This is the test. This is what's on your sheet that has your test on it. It says, given a function f, which is continuous, positive, and decreasing, consider the sequence a sub n equals f of n. So all that means is take your function and look at it only on the integer values, 1, 2, 3, 4, 5 instead, right? Restrict that function just to the points along it. Then if the integral from 1 to infinity of the function converges, so does the series. If the integral diverges, then so does the series. So whatever the integral does, the series does. That's what the integral test says, right? It's a great test. It requires we do integration, but it's a great test because you know right away from the answer what's going to happen to the series. So here's how we're going to use the test. If we're given a series, we're going to first convert it to a sequence. And then we're going to, if we're given a series, we're going to convert the sequence to the function f. We're going to make sure that the function is continuous. We're going to make sure the function is positive. We're going to make sure the function is decreasing. If we can do all three of those things, then we can use the test. And that means we have to compute an integral. So when you show a function is decreasing, this is kind of the tricky spot. Back in Cal 1, to show a function is decreasing, you have to just show that the derivative is negative. Remember that positive derivative means a function's going up, negative derivative means it's going down. So when we have to show that a function's decreasing, we're going to have to show that its derivative is negative. So the problem I see with students with the integral test is they have no problem actually doing the integral. Everyone has no problem with this. They're like, yeah, I can do that. But they never do this part. They never check that the function's continuous, positive, and decreasing. They never show it. They just go straight to the integral. And you can't do that. You have to show the three conditions are met to do the test. So let's do an example. I think this is best illustrated if we just do an example here. All right, does this series converge or diverge? All right, so I start looking. Nth term test. Let's let n go to infinity here. N goes to infinity, you get 0. That tells you nothing, right? Is it a geometric? I don't see n as a power. Okay, so it's not geometric. Is it harmonic, constant over linear? The square root messes it up, doesn't it? So it's not harmonic. Telescopic? I don't think so. I don't have a way of splitting that up, right? Like I can't do partial fractions on this. So it's not looking harmonic. I mean, sorry, it's not looking telescopic. So integral test is the only thing we have. But if it's if we're going to do the integral test, I'm going to write it down first. I'm going to try the integral test. The first thing I want to do is convert the sequence to a function. So the part in yellow, I'm going to convert it to a function of x. And my recommendation to you is at this point right now, if you're going to use the integral test, you better be thinking, do I feel like integrating that? Can I integrate that? Because if I can't integrate that, there's no sense in me trying the test, right? That is something you should all feel very comfortable integrating. It's a basic U substitution. We'll do it when we get to it, but that should be something that doesn't scare you away. All right, so integral test seems plausible here. So there's my function. First thing, is it continuous on the interval 1 to infinity? Remember, when we do this summation, we're going from 1 to infinity, right? So when we're looking at the function, we're trying to find the area under it from 1 to infinity. We got to make sure it's continuous. Well, where's the only place that we have a problem here? Oh,
-1.
there's more than one place, but we would need, what do you say there, Austin?
-1.
-1 will be a problem. It would also be a problem if this is ever, if the x plus 1 is ever negative, right? It can't be negative and it can't be 0, because then you can't take square root of a negative number. So we would need that x plus 1 to be greater than 0, which means that x would have to be greater than -1, but that's okay, right? X is going to be greater than 1 because we're going to start greater than -1 because we're going to start at 1, right? And go to infinity. So it's good. It's continuous on that interval. Make sense? I have to show that, all right? I have to actually show that. Second thing, is it positive on the interval 1 to infinity? Yeah, I mean, just take a look at it. I mean, it's 1 over the square root of x plus 1. We are only plugging in x values bigger than or equal to 1, right? So if I plug in a positive number here, positive number plus 1 is positive, square root of positive number is positive, 1 divided by the positive number is positive. I don't think there's much to really show other than, yeah, that's positive, right? Always going to get a positive output. 2 of the 3 conditions are held. Questions? The third condition is usually the hardest. Third condition, is it decreasing? Decreasing on the interval 1 to infinity. Well, I need to show that the derivative is negative, right? So here's my original function. I'm going to rewrite the original function like this. I'm going to write it to the -1/2 power. That's the original function. I'm going to write it that way so I can do my derivative with the chain rule. So I'm going to take my derivative. I get -1/2 x plus 1 to the -3/2, right? Isn't that the derivative of that? And if I write that a different way, I could write that as, I don't know. How about I do it this way? -1 over 2 square roots of x plus 1. Doesn't matter if I put the cubed on the inside or outside, I'll put it on the inside. Isn't that what it is? Raising to the -3/2, drop it to the bottom, change the power into a radical. That's my derivative. Is this negative all the time? As long as x is positive, right? As long as x is positive or greater than 1, we're in business here. Because you have a positive number, plus 1 positive, cubed positive, square root of that's positive, times 2 is positive, right? Everything in the denominator is positive. And then the numerator is -1. That's always less than 0. Check. This function is decreasing. Make sense? Now you can use the test. So to do the test, you're going to do the integral from 1 to infinity of 1 over the square root of x plus 1 dx, which if you remember from earlier, the way we do these is we convert the infinity over, we do a limit, we replace the infinity with t, and then we do this. That look familiar? I need an antiderivative. So you would have to go figure out the antiderivative of this. Maybe you do that on the side. I'll do it over here. If I do the integral, the indefinite integral, so just do this over here. I can do a basic u sub, u is x plus 1, du is dx. And this gives me, okay, this gives me integral 1 over root u du, which I can rewrite as u to the -1/2 du, and the antiderivative of that should be, what is the antiderivative of that? U to the 1/2, but a 2 out front, right? So 2u to the 1/2 plus a constant. So 2 square roots of u is what it is. So this becomes equal to limit t goes to infinity. All right, here we go. The antiderivative of this we just figured was 2 root x plus 1, And we're evaluating that from 1 to t. Right? And plug in t, limit, t goes to infinity. We get 2 root t plus 1. And then that's what we get when we plug in t, and then minus 2 root 2. And now let t go to infinity. And do you see what happens? This thing blows up and goes to infinity. This goes to a number. Infinity minus a number, infinity. This diverges. Diverges. Okay, make sense? I'm not done. Therefore, the sum n equals 1 to infinity of 1 over the square root of n plus 1 diverges. By the alternating series test, by the integral test. Now, I don't need to say that I drew this conclusion because of the integral test, because I stated earlier, right, in the very beginning of this, I put integral test, right? I let everyone know I'm about to run the integral test. I converted the sequence to a function, checked the 3 things, integrated it, I did a little antiderivative here, found out it diverges. The theorem or the test says whatever the integral does, the series does. You thought you were done with integration? No, you didn't think that, did you? How y'all feeling? All right, looking at this one. Does it converge or diverge? All right, well, look. Nth term test. What about the nth term test? If I let n go to infinity right now, I get infinity on top and bottom. So I do L'Hopital 1 time. Take derivative of the top, I get 1, derivative of the bottom, let's derivative e to the n. E to the n, so you get 1 over e to the n, that goes 0, you know nothing, right? Is it geometric? If the n up top wasn't there, if that was 1 over e to the n, it would be geometric, right? Think about that. If this was sum 1 over e to the n, then I could rewrite that as sum 1 over e to the n, couldn't I? And then that would be my r. And so I'd have to mess with it. I would have to mess with it because, remember, I need it in order, if this starts at 1, for it to be geometric, that needs to be an n minus 1 for me to figure it out. But right now, just what's in red here, does that converge or diverge? Don't tell me what it converges to, or, you know, it converges, right? We could figure out what the sum is, but we'd have to mess with the n minus 1. But right now, you could tell me it converges because you already know what r is. R is this. 1 over e is smaller than 1. So you know that's convergent, right? If that was our series, that's not our series, okay? What messes it up is that n up top. The n up top screws it all up. So it's no longer, it's not a geometric, right? So not geometric, it's not harmonic, right? Not a constant over linear. Telescopic, I don't see any way to rewrite that so we get subtractions in there. Integral test, can you integrate that? Think about that as a function of x. Can you integrate it? Integral test. I'm going to convert it to a function of x. X over e to the x. I'm going to rewrite that as x e to the negative x. I'm going to bring that e to the x up top because I think if you write it this way, this might be a little bit easier for you to think about how you would integrate this. Anyone see how we would do this? By parts. Integration by parts. Okay, well. All right. Right there, you all right? What would your U be though? If you tried just basic U sub. Yeah, no, this is gonna take, well, I don't remember the test, to tell you the truth. No, you have to do, because if you try a U sub, there's no U you could plug in that would make that easier. Yeah, U would, the only thing you do is use X, but then it would just turn into U, e to the negative U. Yeah, so it's going to be parts, but look, before we even get to parts, we have to show the other things, right? So first of all, is this continuous? Yeah, because look, if you plug any numbers in here, right, you're never going to have any problems. No division by zero, no issues, right? You're continuous. How about positive? Well, your numerator is X and your denominator is e to the X, right? E to the X is always positive. But X could be negative, but remember, where are we looking? Only from 1 to infinity, right? So this will always be a positive value coming out of there. What about decreasing? We have to see if it's decreasing. That requires something, right? What do we have to do? Take the derivative, right? So is this decreasing? So let's do our derivative. I'm going to use quotient rule. You could do it either way, but I'm not going to use this one that I boxed. I'm not going to take derivative of that. That would be product rule. I'm going to do quotient rule instead. That's just my personal preference here. Derivative of top times the bottom minus derivative of the bottom times the top all over the bottom squared. I need to make sure this is a negative number, right? So if I look at the numerator, I can factor an e to the x out. And I get 1 minus x up top. And on the bottom, I've got e to the x, that squared. And I think I'm done. Because e to the x is always positive. So that's a positive number. E to the x squared is going to be positive. These are positive, right? So all that really matters is this. And where are we starting our x at? 1. So when we plug in 1, we get 0. That's not negative, right? But if you go anywhere past 1, like 2 or 3 or 4, this is going to be negative, isn't it? So initially it's 0, but once you go past 1, it's going to start diving down, which is all we need. So this is less than 0, check, for x greater than 1. So we're in business. We have a decreasing function, right? So we can do our integral. Integral 1 to infinity. X, now I'm going to integrate it in this form. Here comes my integration by parts. So I'm going to choose my u to be x because in the new integral, it's going to get nicer. And then that forces my dv to be e to the negative x. Don't forget the negative dx. The antiderivative is negative e to the negative x. And so I know when I rewrite that integral, it's going to be negative x e to the negative x. That's ultraviolet. That's those two multiplied, minus the integral of voodoo, which is negative e to the negative x dx. Is that okay with everyone? Negative x e to the negative x plus the integral e to the negative x dx. I just pulled the negative out. And now I do the antiderivative e to the negative x again, which I already did once in this problem. So I'm going to get a negative e to the negative x again, plus a constant. So that's my antiderivative work on the side. All right, I'm going to do something before I even mess with this. I'm going to pull the e to the negative x out. And let me pull a negative e to the negative x out, and I'll be left with x plus 1 there, wouldn't I? Isn't that what I would get right there if I pull that out? And then I'm going to do one more step. I'm going to do x plus 1 on top, and on the bottom, I'm going to put negative e to the x, like that. I'm just choosing to do this because the reason I'm doing this, okay, the reason I'm doing this is because right now, if I ask you to let x go to infinity here, right? Because isn't that what we're going to wind up doing here? Aren't we going to let something go to infinity? This is kind of messy to look at. if I let this go to infinity, but here it might be a little easier to work with. Maybe use L'Hopital. Let's see. You ready? Bless you. So here's what I'm gonna do now. I'm gonna do something I have not done in this class. All right. This is the first time I'm ever gonna do this. I'm going to do the antiderivative. Evaluated from 1 to infinity. Normally I do limit, right? Limit t goes to infinity, and then I replace that infinity with t, and then I do a limit. I'm going to not write that anymore. And I'm going to understand that the next step, when I plug infinity in, I'm taking the limit. Okay, I'm going to understand here that what I'm doing is like, I'm going to plug infinity in for x, which is going to really be a limit. And then I'm going to plug 1 in. Let me do the 1. That's going to be easy. Negative e to the 1. There's what I get over here, right? So this goes to this. Just plug in 1 here. We get 2. Plug in 1, you get negative e. But now think about what happens as I plug infinity in for x here and here. What do I get on top and bottom? Infinity on top, right? Infinity on the bottom. Well, negative infinity because there's a negative in front. So I could use L'Hopital, couldn't I? So a quick little mental L'Hopital of that would give me 1 over negative e to the x, wouldn't it? That's what L'Hopital will give me on that. And now let x go to infinity, and what would you get here? 0, right? Fixed number on top, bottom goes to negative infinity, that goes to 0. And so what we get at the end is 2 over e, because you have a double negative here. So what? Converges, right? This is convergent. That's a number. 3, you all right? What's wrong? I'm going real fast. Yeah, this pace is going to be the rest of the way in this class. I understand it's a lot to absorb. Glad we get it to record it, just in case you need to go back. But what's going on? What do you got going through your mind here?
How did you get to L'Hopital?
Okay, so right here, what I'm saying to you is that I'm going to stop writing limit. I'm just going to put infinity in here. So when I put infinity in, I don't really mean plug in infinity because you can't plug infinity in. But I'm thinking to myself, what I'm really doing is I'm letting this x go to infinity and that x go to infinity. If this goes to infinity, I get infinity plus 1, which is infinity on top. And then if I do e to the infinity on the bottom, I get an infinity on the bottom. I'm just not writing any of it down. Yeah, but I understand. That's why I prefaced it with, I've never done this before. We just don't have time for it. Okay, like we as in, like when you move on to other classes, you just don't have time within problems sometimes to, like in most books, as you move on, you will go, I mean, they will go from this right here. This is what they'll put, and then they'll put this answer. Everything else is up to you. All right. So we're trying to kind of trim out some of this little ancillary work that we need, trying to speed it up. So I did L'Hopital on that, got 0. That okay? Make more sense? Okay, I'm not done. Therefore, the original series, right? The original series, n over e to the n does what? Converges. Converges to what? We don't know. Okay? The area under the curve converges to 2 over e. Our series converges to some number less than that or equal to it. We don't know. We don't know what it converges to. We just know it converges. So don't make the mistake of thinking that your series converges to the same thing that the integral converges to. Remember, there's a bunch of rectangles underneath the curve. There was a bunch of gaps in there, right? So we haven't accounted for the gaps. Questions? Whew.
That was the fourth rule, right?
Fourth rule?
The last one?
Fourth rule?
Yeah, that one.
Oh, you're talking about the series tests?
Where 1 to infinity.
Are you talking about this? Or no? What were you saying? Fourth rule?
Was the number 4?
Show that f is decreasing, that one?
Yeah.
Is that what you're talking about? We did show f was decreasing right here. So if you're following, these steps 1, 2, 3 are not coinciding with the steps there. If you want to coincide there, the first thing we do is convert it to a function of x. Then we show it's continuous. Then we show it's positive. Then we show it's decreasing. And then you do the integral. Is that what you're trying to do? Match it up to the steps on that page?
Okay,
Yes?
yeah.
Okay. I put 1, 2, 3 because whenever you do integral tests, you always have to show those 3 things first. Those 3 things have to be shown: continuous, positive, decreasing. All right. I had the sheet up here. We may as well look at that real quick. So here's the sheet that you're allowed to have on the test. You're welcome. Nth term test, right? We've got that. We've had that for a while. We should know how to handle geometric series, you know, what it converges to, right? We know that. We know the form. By the way, right here, I am more than happy to let you write into that formula sheet sum n equals 0 to infinity, a r to the n. The other alternative formula, feel free to put that into the formula sheet. What else have we done here? We've done the integral test right here. Anything else on here we've done? Nope. That's it. That's where we are. Got a little bit of work to do still. All right, we're moving on. I've got 9 minutes. All right, your next series that you should be able to look at and recognize is called a P series. And the P stands for power. Okay, it's a power, basically a power series. What it is a P series is a series that has this form right here. Sum n equals 1 to infinity, and then you have n, now n is the index, right? N raised to some fixed power P. So if I start out, let's say if I let P, well, I'll do examples. Well, let's do an example. How about this one? What if I do a P series with P being 2? If P is 2, then the series will look like this. Sum 1 over n squared. N equals 1 to infinity. That's what a P series with P being 2 would look like. And if you write it out, it'd be 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. Make sense? If it was a P series P3, it'd be 1 over 1 cubed, 1 over 2 cubed, 1 over 3 cubed, 1 over 4 cubed. Notice that these are not geometric, right? The n is in the base, not in the power. Now, I'm not going to get into a detailed proof on this. Okay, I'm not. I'm just going to tell you what the results are. And a P series is actually nice. Kind of like, you know how harmonic was nice? All harmonics diverge. P series works in a similar manner. If the P is bigger than 1, you've got convergence. If P is less than or equal to 1, you've got divergence. Right? I'm not going to prove it. We just for time's sake. We can prove it. Guess what we use to prove it? The integral test. We take an arbitrary value of P and we do an integral on it. And then we wind up falling back on a rule we developed earlier in the semester. So I'm not going to show the proof of this. We won't prove it. All right. Oh, I asked how you do it. It says it right here. All right. This is the next little animation is just to show you that it does work. It just, you can, I had the computer here actually computing the sum of the sequence for me. And if I change the value of the power, right now it's 1 over n squared, it's going to converge to this number. But if I change the power, watch, if I change it, 5/2, see, all of those, what's P here? What's P on this P series? 3, that's bigger than 1, right? We get convergence to 1.20206. If I let n equal 7/2, it's still bigger than 1, we get convergence. 4, still convergence. 5, still convergence. It's what happens when I go the other way. It's, okay, 1 over n, boom, we hit infinity, right? If we go square root of n, we get infinite. We go 1, well, wait a minute, what's that? That's x to what power? That's x to the 0 power, right? And that's just basically adding up 1 plus 1 plus 1 forever. And if I go a negative power, what what would 1 over x to the negative 1 be? It would just be x, wouldn't it? So, or n, I should have said n. So yeah, these are actually off the chart. You can't see them anymore. So simple, it's a simple test. And we have 5 minutes. I think that's probably where we'll have to stop. All right, so now we know where we are. We still have the comparison test. And then after the comparison test, we have the limit comparison test. So I will put together an email. This time I won't forget. I will put together an email sometime in the next couple of hours, maybe tonight, where I tell you like what's the plan for Wednesday. Like I'm gonna have you watch some stuff and give you an assignment. I'll tell you what problems in the book to do. Right? Any questions? How are y'all feeling? Is series living up to its reputation so far? Are y'all feeling, is it not as bad as you thought at this point? Seems, yeah, it seems within reason to, yeah. The integral test could get messy. The challenge is going to be just kind of like it was with when we were doing antiderivatives, was what to use, right? Because really, when you get to your final, you have to figure out which of these tests to use on the series. You're just going to see the series and then you're going to be like, okay, what do I use, right? So it is quite possible you go down the wrong road for a while and then realize, oh crap, that's because some of these tests are inconclusive. You'll see. All right. Y'all have a good rest of your day and check your email soon. Everybody at home all right? Questions? Good.